Hi kids, let's talk about the radius of convergence and how to use the ratio test to get the radius of convergence. So before I start, I want to give you some big ideas. The big ideas being the interval of convergence and the radius of convergence. Even though I've written the interval first, so we call this the ROC, we call this the IOC. We are going to do this first, and the next video will cover the interval of convergence. But I want to remind you that there is a particular series, one of our faves, a geometric series for whom you already know the interval of convergence and can find it, right? So you remember if you have a, first one is an interval of convergence, and the radius of convergence is a number. So the interval of convergence means you have a given function, right? So here is some rando function. And you want to, and then you have its polynomial expansion, or it's the infinite polynomial series representing it. And you want to know on what interval does your polynomial exactly match. Is it -1 to 1, like it is for our geometric series, right? We found if we have a geometric series, the interval of convergence is from -1 to 1. You saw from our Maclaurin series, right, our famous ones, sine of x, cosine of x, e to the x, the interval of convergence is infinite. That's the best case scenario, right? So your interval of convergence gives you values of x that you can plug into your power series and create convergent numeric series, right? The interval of convergence is the values of x that you can substitute in to your power series to create a convergent numeric series. And again, you don't know why, but convergent numeric series is the pot of gold at the end of the rainbow. That's what we want. Convergent numeric series. So the radius of convergence is just the number that says how far from the center does the IOC go or reach. And I want you to think absolute value when I say how far. How far from the center? So for example, down here, you can see with the center at 0 that I've highlighted, the radius of convergence is 1. How come? Because I can go to the right from the center, a distance of 1, and to the left of the center, a distance of 1, and that's where I can pick all of my x's that will create a convergent numeric series. If I had the function sine, its infinite polynomial matches it exactly from -infinity to infinity. That's the interval of convergence, and in that time, the radius of convergence is infinite. Okay? So that's the big idea of where we're going. So we are today's homework, and your homework is a handout. You are just going to be giving me a number or infinity. You're going to tell me you can go 2 units to the right and left of the center, or you can go a half of a distance from the center to the right and to the left, and those are the values of x that you can use. We are going to start, though, with the ratio test for a numeric series, and we're going to use this test to branch off into what we're going to do for infinite series, for power series, excuse me. So you remember that geometric series have a constant ratio between the terms. Other numeric series have ratios that are not constant. Here's where the ratio test starts. If the absolute value of the limit of the ratio between consecutive terms is less than 1, then that non-geometric series will converge. You need to add this to your list. Hopefully you have a list of geometric series, P series, nth term test for divergence, right? I'm going to write it out a little bit more in more mathy terms. For a series, a numeric series, a to the n, where, right? And a to the n, just as your terms, first term, second term, third term, fourth term. If the limit of the absolute value of the ratio of consecutive terms, the second term compared to the first, the 10th term compared to the 9th, if you evaluate that limit, shouldn't have the then there, sorry. If that limit is less than 1, then the given numeric series converges. If that limit is greater than 1, the series diverges. So this is what you need to add to your list, the ratio test for convergence of numeric series. You want convergence. If you fail the convergence test, you are able to say diverges, but the ratio test has one extra caveat. If your limit is exactly 1, dagger, I can't make a conclusion. Don't confuse this with the limit comparison test for improper integrals. Remember that if you evaluated the limit of one function, your known function, to your unknown function, that limit had to be between 0 and infinity, or else it was inconclusive, right? This is the ratio test for convergence of numeric series. Add this to your list. You could use this on numeric series. When you're doing a numeric series that is not geometric and it is not a P series, but has lots of powers, exponents, or factorials in it, the ratio test is a good numeric test to run. We, though, are going to kind of morph this ratio test for convergence of numeric series into a power series test. So remember, this is the ratio test for numeric series. Now, I want to go back to this idea of the radius of convergence of a power series. Remember, that is a number or an infinity. Once a power series has been made, so we've made it with our geometric series, power series form, or our Maclaurin series formula, our Taylor series formula, or somebody just gives us a power series, how can we tell what values of x will create a convergent series? That's, remember, the interval of convergence. We're not going to get to the interval of convergence today. We're just going to get the radius of convergence, which tells you from the center how far right and left can you go. Remember, convergent series are what we're after, so the ideal situation would be like sine, cosine, and e, where any x you can plug in and you will automatically have a convergent numeric series. But if we can't have the ideal, at least I'd like to know which x's I can use. That's what the ratio test is for. But don't forget, please don't use the ratio test if you don't have to. Is your famous series geometric? Is it 3 over 1 minus x, right? If I can identify that common ratio r, as long as I say that the absolute value of that r is less than 1, bam, there's my radius of convergence. Actually, and I straight up just get the interval of convergence from that. Is it Maclaurin or a manipulation of Maclaurin, right? Is it e to the x squared? Is it 3 times sine x? Is it x squared times cosine x, right? These are the series that converge for all x's. I don't need the ratio test. But if I don't have my famous series, I can run the ratio test. The ratio test will prove that I can either use all x's, love, or will give me a set of x's that I can use, or will prove that I can only use the center. This is annoying. A lot of work for no gain. Remember, I want ideally lots of x's. Really, a set of x's is still an infinite amount of x's, isn't it? It's just a smaller range. And then, or it'll give me the worst case scenario, which says the only thing you can use is the center, the point of tangency, and nothing else works. Okay, so I kind of sort of, right, think of this as here's my center. We usually call the center A. How far right and left can I go before I run out of x's that I can use? Okay, that's the radius of convergence. If I say the radius of convergence is 5, then from the center, the point of tangency, you can go 5 units to the right and 5 units to the left, soft brackets, and pick any of those x's. And you will get a convergent numeric series. That's what the radius of convergence says, all from the center. So we are going to use the ratio test. We're going to morph the numeric ratio test on a power series to find all those values of x, or to find the range of values. So here's what the ratio test is for power series. There's the x. Everything else is your geometric series. Do you see it? I'm sorry, your numeric. There's the numeric ratio test. The limit as the number of terms goes to infinity of the absolute value of the ratio of consecutive terms is it less than 1. And the only thing that is extra that makes this the power series is multiplying by the absolute value of x minus the center. This is annoying. I probably shouldn't have used a's in both cases, right? This a so then represents terms. This a is the center. By the way, here's a helpful algebraic rewrite for using the ratio test for a power series. Oops, sorry, I forgot my absolute value thing of the x part. Right? A fraction, a division, is the same thing as a multiplication of the reciprocal. The algebra that we're going to do, you're going to want this form. So if you evaluate this limit, the values of x that satisfy the strict inequality determine the radius of convergence around the center A. AP loves the ratio test on a power series. So let's make sure that we give them what they love. So here's what the directions would look like. Does this series converge? And it would be a power series. Does the given power series or the one you just made converge? And if so, what is the radius of convergence? Remember, when somebody asks you for the radius of convergence, just give them a number or give them infinity. Okay. Finding the interval of convergence when it's not geometric is a little bit tricky, which is why, or I shouldn't say tricky, it has a little bit more work than just the radius of convergence, okay? And it has to do with whether your endpoint, right? Your interval of convergence is open, closed on one end and open on the other, closed, or vice versa, or closed on both. That's a little bit more work. So you like when you're asked for the radius of convergence because it means a little bit of less work. And your answer is just going to be a number or infinity that describes how far from the center you can go to the right and to the left. So step 1, set up and simplify the ratio test limit. There is going to be a rubric point for the setup, I promise. Unless it's multiple choice, there is going to be a point for this. So you best write limit. You best write absolute values. You best write a ratio. You have to write all of that for the setup point. After you simplify with your algebra, simplify it, then suck out the x part, right? You don't want the x part in the inside of your limit. Then evaluate your limit. And then answer this question. Okay, so let's do an example. So the directions that I erased. Does this series converge, this power series converge? And if so, what's the radius of the convergence? So first, talk to me about the center. Where's the center? Right, 5. So my center is 5. So think of this point 5. How far to the right and how far to the left can you go? Can you radiate and pick x's from to plug in for this x and create a convergent numeric series? Now, this is not geometric. It would be geometric if n was 1, right? So the first thing I do is set up the limit. There is going to be a rubric point for that notation, the absolute value notation, and the fact that you have replaced every n with n plus 1, and then multiplied by the reciprocal where you leave just the n's in place. Now notice I've left off the less than 1 so far, right? I really should say this limit is supposed to be less than 1, but I'm going to do the algebra. So I can't osmosis the x stuff out yet. I do. Because I have x, because I have an n here with my x. And I have an n here with my x. But my goal is to osmosis that x stuff out. So watch me do some algebra. Notice what I did here. 3 to the n times 3 to the 1. And what I did with this n plus 1. X minus 5 to the n and x minus 5 to the 1. You see what happens now? Bye-bye. And bye-bye. Right? Notice that what I have left for my x now. There's my x, and it's my x minus my center, and it's just to the first. Osmosis that baby out front. Now, don't forget you have to keep the absolute value bars, though, right? Because it was inside here. So keep the absolute value bars. Now, just evaluate a numeric limit, right? A numeric limit. That's pretend you're in algebra 2 and somebody's asking you for the end behavior of that rational function. What is it? Right? This is n to the first, and this is 3n to the first, so the powers are even, so it's the ratio of the leading coefficients, which is just a third. There is my limit. Here is my x stuff outside of my limit, because my limit only has to do with n. So I only have n stuff in here. I treated it like a right? N behavior of a rational function. That's where I got 1/3. And now I said to myself, okay, now I'm going to remember that I need to be this left side, the limit that I evaluate. I have to take the left side here and make sure I'm less than 1. Well, that actually means that the absolute value of x minus 5, which by the way is the distance from the center, needs to be less than 3. 3 is your radius of convergence. That's how far you can radiate to the right and left of your center 5. If you replace this x with any number strictly between, so don't you dare use 2 and don't you dare use 8, but you can use 1, replace x with 1, you have a numeric series that you don't have to test, bam, you have a convergent numeric series. Replace x with 7.99999, bam, you have a numeric series and it's convergent without having to test it. How many infinite numeric series do you have? An infinite amount, because there's an infinite amount of numbers between 2 and 8. And any one of those values between 2 and 8 can be used to replace the x in the power series, create a numeric series, and it will converge. 3 is the distance from the center 5 that you can radiate and pick any number. Right, so up here, remember, we said the center was 5. How far can you go to the right and to the left? Well, you can go a distance of 3 to the right. You can go all the way up to 8, but don't touch it. And you can go a distance of 3 to the left, which means you can go all the way to 2. Just don't touch 2, don't use 2. Plug those values in for x, boom, convergent numeric series, life is good. Let's do another one. All right. First thing I do is I look at that series. Is it geometric, right? Is it one of my famous Maclaurens? No. I don't recognize it. What's my center? 3. So my center is 3. How far to the right and how far to the left of 3 can I radiate and pick x's to plug in for this x and have a convergent numeric series? So step 1, set up the ratio test. Don't forget the limit, the absolute value, right? And remember, this all has to be less than 1. I just reminded you that what I have here, right? Has to be less than 1. I picked this example has factorials in it. So I want to write the last one had exponents, where I showed you splitting up exponents with like 3 to the n plus 1, make it 3 to the n and 3 to the first. I'm going to have that scenario here too, but I also have to deal with factorials. So look at your x's. Here is an x, here is an x, but it's trapped in the n, this x is trapped in the n plus 1 scenario. Focus on your x's, because after all, your limit is n. I'm sorry, focus on your n's. Right? You want to suck the x's out. So do that exponent trick on there and suck them out. And then do you remember how to deal with your factorials? Right? Do you see what I did? Here's me getting x minus 3 to the n and x minus 3 just to the first. That's going to osmosis out, because the x minus 3 to the n is going to cancel out with that x minus 3 to the n. Do you see what I did with n plus 1 factorial? N plus 1 times n factorial. Why would I do that? Because that's going to go away. Now notice what I did with n plus 1 to the fourth in the denominator. Why would I do that? I made it n plus 1 times n plus 1 cubed. Why? Right? This is an n plus 1 to the first, and so is that. So do you see what I'm doing? I'm targeting everybody in my numerator and denominator. I targeted my x's because I know I want to osmose an x minus 3 to the first out front. And then I focused on who else can I reduce and eliminate from my fraction so that I can more easily evaluate that limit. And remember, my limit does have to be less than 1, or I'm looking for values to be less than 1. So there's me canceling things out, by osmosis. So I osmosis the x minus 3, keep the absolute value, kept my limit. Look at what I have to evaluate with my limit. Keep your absolute value bars. Look at that ratio. Think about algebra 2. That's the left-hand side of the ratio test. And this is the right-hand side. What x is times this limit will make me less than 1. Where did this infinity come from? Right? I have the fraction n behavior as n goes to infinity, n to the 4th over n something cubed, top heavy. I do not have a horizontal asymptote, right? This goes off to infinity. Look at this now. I can't divide both sides by infinity. Stop it. But think about what's happening. What x can you put in here, subtract 3, take the absolute value, and multiply by a really huge number and stay less than 1? There's only one number. Do you see what it is? Right? Only 0 is the only thing that I can multiply times infinity and stay less than 1. What number will create 0? 3. The center. The radius of convergence is 0. You can't go anywhere to the right and left. You can only use 3. And then look what happens when you use 3. 3 minus 3 is 0. 0 to I don't care is 0. 0 times this fraction is 0. That is a very boring series, right? It's just the point of tangency. It is just one point. So this is not a useful, I went through all that work to find out that this is not a useful series at all. Boo. In order for this series to converge, the only number I can replace x with is the center, 3. Not very useful. Now let me ask you this. What if this had been reversed? What if I had ended up, I did all this work, blah, 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 blah. I did all this work and I got n cubed over n plus 1 to the 4th. What would my absolute value ratio be? You know, what would the limit as n goes off to infinity be? This would be 0. Right? What number can you replace x with minus 3, multiply it times 0, and stay less than 1? Turn that frown upside down, honey. Turn that thumb upside other way. Every x would make this equality true. So your radius of convergence would be infinity. That's how we got the radius of convergence of sine and cosine and e. The math involved, the ratio test was a little more difficult to work with those, but nevertheless, that's where that came from. You won't be asked to prove those radius of convergence yet, but you will on things like this. So as I said, you can get a radius of convergence that is a number, and maybe that number is 0, which is what you don't like, right? Or you get an infinity, which makes you really happy because that means you can radiate everywhere, as far as you can go, to the right and to the left, and get a good x. All right, last example. This time I wanted to do an example with this alternator thing in here. And I basically want to tell you not to worry about it. So here now, this is, you see I'm starting to cheat a little bit, right? And I'm going right to my setup, right? I kind of stepped it out in the previous examples. I went right to my setup, make sure for the rubric point that you say the limit as n approaches infinity, absolute value bars, replacing your n plus 1s, your n's with your n plus 1s, and then keeping your n's. Make sure you have less than 1. Notice I didn't highlight my alternators. I mean, I went ahead and I typed it in to show you what happens, but you don't need to worry about them. Why? Why don't you have to worry about these sign alternators? Do you see? Yep. Because of the absolute value bars, right? Who cares about them? Right? I'm going to end up taking the absolute value after everything. And so who cares about my sign alternators? Any negative term would just be positive, correct? When I took the absolute value. So I don't care about that. So when you're doing the ratio test, you see a sign alternator, you can just forget about it from the very beginning. I replaced the n here with n plus 1. I replaced this n with n plus 1, and then I multiplied by the reciprocal. Right? So n was in the denominator, is now in the numerator. X minus 1 to the n was in the numerator, is now in the denominator. Do your exponent work. Remember, target your x's. You want to target the x's to be able to osmosis it outside. You can't osmosis it yet because there's an n with it. Do your exponent trick to get rid of it. Bye-bye. Osmosis that x minus 1 to the outside. Evaluate your limit. What is this limit? As n goes to infinity, you have an n to the first and another n to the first, so it's the ratio of the leading coefficients, which is 1. What's your radius of convergence? 1. From where? By the way, where's my center? I forgot to ask you. So this is my radius of convergence. That is a distance, absolute value distance from the center. What's my center? Go up to the original. You can see hopefully that my center is 1. So when you think about the point of tangency being right there, how far to the right and to the left can you go to pick x's? You can go a distance of 1 to the right and a distance of 1 to the left. Choose any of those x's. Replace this x with any of those infinity of numbers, and you will get a convergent numeric alternating series. Cool, right? All right, we will do more examples in our next live session.